All right, so the first thing you're going to do is change this to read 10-1. So this is actually 10-1. Y'all got that, right? Switch it, change it. It's not part of chapter 9. Oops, I didn't want that either. Somehow this became really big. All right, so we're just going to look at the probability of events. Nobody should be talking while I'm talking, or we're going to move back to our original seats. So we're going to use the probability of an event, which you learned in Algebra 1-2 and Algebra 3-4. So it's always favorable over total outcomes, always. And so we worked on outcomes in Chapter 9. So let's look at example 1a. So if two coins are tossed, what is the probability that they both land heads up? So in order to do this, you have to consider that every event has a probability to it. An event would be tossing a coin, spinning a spinner, pulling a card out of a deck of cards, picking a number out of a box. Those are all events. And every time you spin or pick a number out of the box or roll a die, those are all separate events. And so we want to find the probability of event. There are different ways that we can do that. So two coins are tossed. We've got the first coin. We're going to multiply all of its outcomes to the number of outcomes on the second coin. Aren't these independent of each other? What I toss on one coin has no effect on the other coin. And so how many outcomes are there on coin 1? 2. And there would be 2 outcomes on coin 2. So that gives us a total of 4 total outcomes. The question is that I want to know what's the probability that both will land heads up. So there's 2 ways you can do this. You can either make a Punnett Square, which I'm going to do here, or a tree diagram, which I will also show to you. So the Punnett Square on one side here, you're going to put all the possibilities on one coin, and on the other side all the different outcomes on the other coin. So I can have either a heads or a tail, or I could have a heads or a tail on the other coin, right? And then put them together. You're not zoning out on me. You're going to stay with me. But you're not writing. You should be writing and looking. So one of your outcomes is heads, heads. This outcome would be heads, tails. This outcome would be tails, heads. And this outcome would be tails, tails, right? How many of those outcomes is favorable? Only 1 out of the 4. You could have also done this with a tree diagram. So we could have had first coin, and then we would have second coin. Your options on the first coin are heads or tails. And then if you chose, if you flip the coin and you got heads on the first coin, well then the second coin, when you go to flip that, you can have a choice of heads or tails as well. But if you flipped it tails on the first coin, the second coin, you're still going to have a choice of heads or tails. So your final results for each of these are going to be heads, 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 tails, or tails, heads, or tails, tails. Didn't I get the same outcomes on the tree diagram as I got on the Punnett Square? Right? And so the probability that I will have heads, heads turned out to be 1 favorable out of 4 total. So my probability for flipping heads, heads is 1/4. Now that can be changed into a decimal, which would be 0.25, and then from there to a percent, which is 25%. You have to look at Math Excel and see what they want. I always prefer the fraction. It's always the exact. Any questions about that? When you do Punnett Squares, you don't have to have the exact outcomes here as you have here. So if you were flipping a coin and spinning a spinner, like maybe there was 3 colors on the spinner, you could have blue, red, and yellow here, and then you could have your heads in blue, heads in yellow, heads in red, you know, there, and tails, blue tails, red tails, whatever. I missed one. Yellow, I guess. And then you could also do the same thing with the tree diagram. So it's just whatever you're comfortable with. Sometimes a tree diagram gets really big, and so that's my only complaint about that. All right, so let's look at B. So for B, a card is drawn from a standard deck of playing cards. Notice they don't tell you how many cards are on the deck. How many cards are on the deck? You're supposed to know that. So there's 52 cards. The question is, what is the probability that it is an ace? So I want to know, and here's your shorthand probability that you draw an ace. So we want favorable out of total. How many total aces are in a deck of cards? 4. So we have 4 favorable over how many total? 52, and if that can be reduced, do so, and it does reduce to 1 in 13. So you have a 1 in 13 chance. All right, C. C is going to require a little bit of work on your part. 2 6-sided dice are tossed. What is the probability that the total of the 2 dice is 7? So if I were you, I would make a Punnett Square, or I'm going to make a chart, because, so here's what my chart's going to look like. So I'm going to have 1, 2, 3, 4, 5, 6 over here, and then I'll have 1, 2, 3, 4, 5, and 6 over here. And then you're going to put your choices together. So I've got 1, 1. I don't know if I'll put the commas in there. So I got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so forth. So you're going to finish filling out your chart. So fill out your chart. No. You could, but I wouldn't. Because you can use this for other things as you go along. Because they won't always do just a sum. They'll do some different things with them. So as you look at this, look at your diagonals. So as I go along a diagonal, so I can create diagonals this direction, or I can create a diagonal, whoops, going this direction, going this way. So no matter which direction you're going, you can look at your sums. So for instance, there's only one sum for 2, 1 and 1. And as you look along this diagonal, those are the sums for 3. 2 plus 1 is 3, 1 plus 2 is 3. 3 plus 1 is 4, 4, 4, and then we get 5, 5, 5, and so forth. So you want to find, and it's always on a diagonal. So if I were you, I would circle the diagonal that has your sums of 7. So here's that diagonal here, or highlight them. I can't highlight off of this, so there's my diagonal with my sums of 7. So if I have a probability where I want a sum of 7. How many favorable do I have? How many favorable sums? 6 out of how many total sums? And how'd you get 36? Yeah, so if you take 6 possibilities times 6 possibilities, that gives you 36. So we have a total possible number of outcomes of 36, and that does reduce to 1 in 6. So you have a 1 in 6 chance. What's the probability of the total being 2? How many favorable? 1 out of how many total? So it's a 1 in 36 chance. What is the probability that the total will be 13? 0. There are no favorable outcomes out of 36. So 0 out of 36 is a 0 probability. Omni? Are you sure? And yeah, go ahead, ask a question.
No, I wasn't.
Oh, okay. I thought you were raising your hand.
No.
So it depends on how they ask a question. They could ask you, what's the probability that the sum will be less than 5? Does that include the sum of 5? Less than. So it would include the sums of 2, 3, and 4. So you'd add all those up together as favorable. So there's just some possibilities. Look at D. So this is always an interesting one. In a state lottery, a player chooses 6 different numbers from 1 to 40. What is the probability of winning the top prize? So the first thing I need to know is how many total possible outcomes are there for the lottery. So step 1 is going to be our total outcome. 1 to 40? What number?
So like,
I'm trying to
6.
find the total possible
I want
outcomes.
to be different numbers, so I can't put 6, 6, 5, 5.
Right, because with the lottery, and that's a good question, with the lottery, when you have the numbers 1 through 40, you're not going to be able to repeat any numbers. And once you choose a number, that number is taken out. But couldn't I grab a handful of numbers, right? So how many numbers do I have to choose from? 40. And I'm choosing how many? 6. Does order matter?
Yes.
No. Order of my numbers doesn't matter. How I write them down does not matter. That's still a winning hand. And so, is that a combination or a permutation? It's a combination. So we have a combination of 40 items taken 6 at a time. So the shortcut is to write only the first 6 numbers of the 40 factorial. Whoops, not 40. All over 6 factorial. So I'm going to cancel my 6 into 36 6 times. I'm going to cancel 5 into 35 7 times. And I'm going to cancel 4 into my 40 10 times. And then I'm going to cancel my 3 and my 2. The 3 and the 2 can cancel the 6 out. So that leaves me with a 10, a 39, a 38, a 37, and a 7 to multiply. So when you multiply all of those together, you should get 3,838,380 total outcomes. Does that answer the question? Is that what the question's asking? Mm-mm. So the question wants to know the probability of a winner. How many winning combinations are there? How many favorable winning combinations are there out of that 3,800,000-some-odd? One winning set of numbers, right? Because they're all different. So there's one favorable out of 3,838,380. Is that a high probability? If you divide that out on your calculator, you get 1 divided by, whoops, oh yeah, 380. That is 2.61 times 10 to the negative 7. That means that you have 6 zeros in front of your 2. That's less than 1%, quite a bit less than 1%, isn't it? Do you know that only poor people tend to play the lottery? Well, it'd be like you playing the lottery and winning $1. Is that exciting? No, I mean, it's not going to really could buy a soda with that, right? So typically rich people don't play the lottery because they don't need to, number one, and number two, they know that the probability is low. Do you know what the probability of lottery winners are of keeping all that money?
Not high at all.
Oh, it's not high at all, you're correct. So most, because oftentimes people who don't grow up with money, and this is just a generalization, oftentimes people who don't grow up with money don't know how to handle money. And so if you don't go to a financial specialist to help you handle the money, you've got people coming out of the woodwork going, can you give me some money? You got all that money, why won't you give me money? It's not even people that you like. And so you feel bad, and so you start giving out money or you just spend it. You can spend $1 million quite quickly. You would be shocked. I could probably easily spend $1 million in a day. I'd buy a real nice car or a house, right? I could easily do that, couldn't I? And your money would be all gone. And so, be careful. Note to self. All right, so let's look at the second page. So flip it. All right, so we're going to look at the probability of the union of two events. When you're looking at the probability of two things occurring, and notice that the words say or. Well, maybe I'll erase that. Let's underline it. Or is a very important word here. It's not A and B occurring, it's A or B. So there's two different probabilities or two different ways to approach the probability. You either add the two different events, the probabilities of the two different events together, and then subtract the probability of the events occurring at the same time, which is what this is saying here. That's the probability of the events occurring at the same time. Or you just add the probabilities of the events together. How do you know which? Well, if the events can occur at the same time, you have to subtract that out because this is asking for A or B. It doesn't want them both occurring at the same time. So, how do I want to write that? This is the probability when two events occur at the same time. And it could be more than two events. I'm just saying two events for here right now. So for instance, you're thinking, well, what's an example of that? So an example of that could be if you're drawing out cards from a deck of cards, and I want to know what's the probability of an ace or a spade. I don't care what you pull out, but I want it to be either an ace or a spade, but not both, because that's what the word or means. Is it possible for an ace to also be a spade? Yes, it is. There's something called the ace of spades. So you would take the probability of an ace. How many aces are there in a deck of cards? 4 out of 52. Plus, what's the probability of selecting a spade? 13 out of 52. Minus, how many ace of spades are there in that deck? 1 ace of spades. You'd have to subtract 1 out of 52. And then that would give you a probability. If you could reduce it, then you would. If the events are mutually exclusive, that means the events cannot occur at the same time. Whoops. So using cards as our example, What if I asked you to draw out an ace or a number 5? Can those occur at the same time? Can an ace also be a number 5 card? No, because they're both numbered cards. So in that case, you would just find the probability of an ace, which is still 4 out of 52. What's the probability of drawing a 5? Also 4 out of 52. Total probability 8 out of 52, and then you would reduce. So there's nothing to subtract because they can't occur at the same time. Okay, so let's look at an example. 2. What is the probability of getting a 5 or a 6? A 5 or a 6 when you throw or roll a dice. So it's important to realize how many outcomes are on a typical die. 6, 1 through 6, right? And so we want to find the probability of rolling a 5 or a 6. Can you roll the die and get both a 5 and a 6 popping up at the same time? So these are mutually exclusive. They cannot occur at the same time. So these cannot. So therefore, I'm just going to add their probabilities together. What's the probability of rolling a 5? What's the favorable? 1 out of how many total? 6. Then add to that 1, because that's the probability of rolling a 6 out of 6. The reason why we're not multiplying the probabilities together is because we're having one roll. It's one event. And in that one event, I want to have either a 5 or a 6. If I were rolling that die twice, and I wanted to know what's the probability of getting a 5 and then a 6, that's different. This we're adding because we have one event. So make sure that you realize the difference. So then I get 2 out of 6, which reduces to 1 and 3. Example 3. What is the probability of drawing a heart or a face card out of a deck of 52 cards? Can a card be both a heart and a face card? Yes. So these can occur, emphasis on the word can, occur at the same time. So we want to find the probability that we have a heart or a face card. So FC for face card. So what's the probability for drawing a heart? How many hearts? 13 out of how many total? 52. Plus how many face cards? 12. So how many suits are there? 4 suits. Spades, clubs, what else? Hearts and diamonds. So there's 4 suits. Each of those 4 suits has how many face cards? 3, a jack, a queen, and a king. So 3 times those 4 suits is where the 12 face cards comes into play, and you are responsible for knowing all of that, which we went through last week. But then I had to subtract out the possibility that they can occur together because I want one or the other, not both. So how many hearts are face cards? 3. There's a jack, a queen, and a king of hearts. And so we're going to subtract out 3 out of the 52. That gives us 25 minus 3, which is 22 out of 52, which reduces to 11 out of 26. So again, the difference between example 1, those 4 examples, and then example 2 and 3 is, for example 2 and 3 only have one event that we want to see more than one thing occurring, versus example 1 has multiple events occurring. So look at the last page. We're going to look at independent events. The probability that A and B will occur is, and here's where we're going to multiply those things together. So independent events means that we have different events occurring. So it's multiple events versus the last two examples was one event. This is, again, multiple events. So you see us multiplying those probabilities together. And they could be different things. Spinning a spinner, rolling a die, tossing a coin, picking a number out of something, that kind of thing. Those are events. Independent events just means that what happens on one event does not affect what happens on the second event. And so we'll just multiply those events together. So look at example 4. A computer selects 3 integers from 1 through 20 at random. What is the probability that all 3 numbers will be less than or equal to 5? So this is unlike the lottery one, where when we pick out a number, it's set aside. Can't use it again, right? Whereas this one, I could go 111, 222, 333, couldn't I? They don't say anything about repeating here. So the assumption is that every time I pick a number, it's from the same group of numbers 1 through 20. They don't mention anything about not being able to repeat. So I'd like to, first step, find the probability of each of these events separately, because they're all fairly identical. The question is asking, what's the probability that all 3 numbers will be less than or equal to 5? So probability that every number that's chosen is less than or equal to 5. So this is just for one event. How many numbers out of the 1 through 20 have a favorable value that's less than or equal to 5? 1, 2, 3, 4, 5. So there's 5 out of 20 total possible choices. And doesn't that bring us to 1 in 4? So you have a 1 in 4 chance of choosing a number that's less than or equal to 5. So to actually find the probability that all 3 numbers are less than or equal to 5, we've got our first number times a probability for our second number times a probability for our third number. So the probability for our first number, isn't it 1 in 4? So we just came up with that. And the second number is also 1 in 4 because they're all identical. They're all independent of each other. One does not depend upon the other one. So what does that equal? Multiply. Yeah. So be careful there. So we got a 1 in 64 chance. And if it's multiple choice, you know they're going to have 1 in 12 as a choice, right? Yeah, so be careful. So that makes sense, right? Separate events, multiply their probabilities together. If they were dependent, what if I said here that the numbers would be less than or equal to 5, but you can't repeat the numbers, so you can't have 1, 1, 1. How would that change how you would do this? This would still be 1 in 4, wouldn't it? What does this one become? How many favorable choices now would there be out of the 20? You use one of them up because you assume the first one came out to be less than or equal to 5. So what would this one be? Well, how many choices? I had 5 originally and I used 1 over here. So wouldn't I have 4 out of, would I have 20 or would I have less than 20? 19. Because you use one of them and set them aside. And what would this one be? You have to assume that both numbers turned out to be less than 5 or equal to. So how many now? Use 1 here, use 1 here. How many now? 3 out of, you've used 2 numbers, so it's out of 18. So that's how the dependent events would work. Let's look at the probability of a complement. Oftentimes it's easier to find the probability of something if you find the probability of its opposite. So if I wanted to find the probability of drawing an ace, we already found that that was 4 out of 52, but sometimes we might want to find the probability of not drawing an ace. How many cards are not an ace in a deck of cards? Well, if 4 are an ace, then 52 minus 4 is 48, so 48 out of 52 would be the complements, which would be not drawing an ace. So that's really what a complement is, and that's what we're going to use here. So a complement is really, you could take 1, which is 100%, and subtract out the complement, or the opposite of what that is. So if I wanted to find the probability of drawing an ace, I could find the probability of not drawing an ace, which would be 1 minus that 48 out of 52. That's still going to give me 52 out of 52, which is 1, minus 48 out of 52. Doesn't that still give me 4 out of 52? You're like, well, that seems like a more complicated way. But in some problems, it makes it easier. Because maybe you know how to find the probability of one, but you're having trouble finding the probability of the other side. Are you paying attention? Just checking. Focus with me. So then step 1, this has 3 steps to it. So then our first step is going to be the probability. Oh, well, let's look at the problem first. A manufacturer has determined that a certain machine averages 1 faulty unit for every 1,000 it produces. So what does that mean? 1 faulty unit for every 1,000. So how many are perfect? 999. That's pretty good, right? What is the probability that an order of 200 units will have 1 or more faulty units? So sometimes it's just easier to find the perfect units and then use that probability to find the faulty units. So for our first step, we're going to find the probability that any given unit is perfect. Okay, so the probability that 1 unit is perfect is what? We talked about that. What is that? 999 out of 1,000, right? So we're going to use that. And then step 2, let me move this up a bit. Step 2, we're going to find the probability that all 200 units are perfect. Look at the fact that each unit is considered an event. So the probability that 1 unit is perfect is 999 out of 1,000, right? So if you go back and look at what we did up here with the numbers, each of these was an event, right? And they happen to be the same event. That's no different than these 200 units that we're producing down here. So I'm going to take that 999 over 1,000 and multiply it to itself how many times? How many units am I looking at? 200. So we're going to take that 999 out of 1,000 and we're going to raise that to the 200th power. Now you're not going to actually find that right now. It's actually going to be a decimal that's less than 1 because you're taking 999 over 1,000, which is a fraction less than 1, and you're raising it to an exponent. It's going to be a number less than 1. It's like 82% or something. All right, so then step 3. So now we know the probability that all 200 units are going to be perfect, but is that what I want? Yes or no? What am I trying to find? That at least one of the units is faulty. So your last step is, therefore, the probability that at least one unit is faulty is. So what we're going to do is we're going to take 1 and subtract the complement. So we're going to subtract the 999 over 1,000 raised, to the 200. And that gives you approximately, so if you punch that out on your calculator, you get about 0.1814. So percent-wise, what's that? It's about 18%, which you're thinking, well, if that's a washing machine, that's no big deal. I have an 18% chance that my washing machine stinks. What if that, don't pack up, what if that's a pacemaker in your chest? Is that a good faulty rate for a pacemaker in your chest?
No.
Not at all. Not at all. In fact, I want my faulty rate to be way, 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 way less than 1%. Because in order to fix a faulty pacemaker, you'd have to go in and have surgery, or that faulty pacemaker could kill somebody, right? So the probability that it's faulty is good or bad depending upon what we're talking about.